We'll take a look now at the basic statics of suspension bridges in preparation for doing the homework assignment on the George Washington Bridge. You remember, I hope, this diagram of the Menai Straits suspension bridge and its load path, which shows that the load generated by a truck at midspan is carried in tension up the main cables, over the top of the tower, and down to the anchorage, and that some of that load then goes into compression in the towers and eventually down to the foundation. We can see in Roebling's Niagara Bridge here that he adds stays below the deck here that provide some level of ambiguity to the load path. In other words, we're not exactly sure with these stays below the deck, and particularly these typical Roebling diagonal stays above the deck, how load is being carried, whether it's being carried from this point, for example, through the diagonal stays or up to the main suspension cable. We've also looked at the idea of the free body diagram when we looked at the Eiffel Tower, and now we're going to develop free body diagrams for suspension bridges. And we'll begin with the Brooklyn Bridge here, a photograph of half of the span of the Brooklyn Bridge here at the top, and then a diagrammatic version of the Brooklyn Bridge half span at the bottom in free body diagram mode. And of course, a free body diagram is simply a sketch of all or part of a structure detached from its supports and with all of the forces acting on the structure shown clearly. So this set of blue arrows here indicates the gravity load or weight of the bridge itself or traffic acting on the Brooklyn Bridge. This red arrow is the cable tension at midspan, this red arrow the cable tension at the anchorage, and this vertical red arrow the tower base reaction. We can now identify some of the geometric parameters of the Brooklyn Bridge. Here we're looking at just half of the main span of the Brooklyn Bridge. The cable tension is still sitting over here at midspan, the blue arrow still representing the gravity load on the bridge, and the cable tension now shown here at the top of the tower, where the cable passes over the top of the tower on its saddle. There's some geometry that we have to have in hand here. First of all, the cable sag is the distance from where, the vertical distance from where the cable passes over the top of the tower to the bottom of the parabola of the cable at midspan. And this length here is exactly half of the main span length of the Brooklyn Bridge. We, instead of using words to describe those distances, use some symbols. So the main span length becomes L over 2. The cable sag becomes D, shown up here. The cable tension is shown as H here and over here. And the vertical reaction is VB, which occurs at point B at the base of the tower. At the top of the tower, we have A here to label that as point A. Now, the way that we develop statics for suspension bridges is to use the equations of equilibrium and say simply that the moments must balance. The sum of the moments at point A must equal 0 if the bridge is to be in equilibrium, in other words, not moving. This is what the moment equilibrium equation looks like for the Brooklyn Bridge at point A. So again, we're looking at moments or torques or tendencies of the forces to rotate the Brooklyn Bridge around point A. And if you remember that moments are forces times distances, we can see that the first term here, H times D, is simply this horizontal cable tension multiplied by this distance, D. All right? And that moment is acting in a counterclockwise direction, like that. The other term here, WL squared over 8, is perhaps a little bit harder to see if you haven't seen these expressions before. But this is essentially the moment generated by the self-weight of the bridge, or the total gravity load, I should say, of the bridge. Self-weight plus live load, traffic, for example. So W is the amount of gravity load acting per foot of span of the bridge. L over 2 is this span here. And then the L squared and 8 come in because we take this gravity load, lump it as a single point force at half of this half span, and then compute moments through there. And this is detailed in more completeness in the structural study that accompanies the George Washington Bridge assignment. If this is our equilibrium equation, we can solve for H, the cable tension, and find that the cable tension is WL squared over 8D. And this is really the key equation for understanding suspension bridge statics, and we'll talk about this more right now. So this is our, as I said, key equation, H equals WL squared over 8D for suspension bridge statics. And I'm going to define this new quantity R as the ratio of L over D. That's the ratio of the span length of the bridge to the cable sag. And I want you to think about this quantity R as sort of the form or shape of the structure. This ratio of cable sag to main span really is, in profile, the defining characteristic of the shape or form of a suspension bridge. And L on its own over here you can think of as just the size or scale of the bridge. As L gets larger, the span gets larger and the bridge gets bigger. H is how the bridge really functions. How does it carry load? What is the cable tension? And W is the imposed load. So what I'm saying in this series of lines here is that H, the function of the bridge, is really determined by the load being transformed by the scale or size of the bridge and the form of the bridge. And we can see that a little bit more quantitatively in these two diagrams. These are structural analysis models of two suspension bridges with different R values or form values. You can see that in the bottom model, the towers are much higher than in the top model. So the R ratio is quite a bit lower. The load is the same and the span length is the same in these two bridges. And we can see that when we change R, when we make R smaller, the cable tension shown by the width of this blue line is quite a bit smaller. So lower towers lead to higher forces in the main cable, and that's one way in which the form of the suspension bridge affects the forces or function of the suspension bridge.